Welcome to AQA AS Chemistry, Ionisation Energy and Electron Arrangements. This is 1.6 in your textbook on pages 17 to 19. So lesson objectives for today are to define the first ionisation energy and successive ionisation energies, explain the factors that influence ionisation energies, and predict the number of electrons in each shell as well as the elements group using successive ionisation energies. So first of all, some key definitions. The first ionisation energy is the enthalpy change when an electron is removed to form a unipositive ion from a gaseous atom. Sounds complicated, but all it is going from an atom that's in the gas state, it's losing one electron, and it's becoming a single positively charged ion. So for example, Na to Na+. The second ionisation energy is the enthalpy change when an electron is removed to form a dipositive ion from a gaseous unipositive ion. So using the previous example, that would be going from Na+ to Na2+. So you're going from an already positive ion to one that's got a 2+ charge. The third ionisation energy would then be going from a dipositive to a tripositive, etc., etc. And all of these ionisation energies are measured in kilojoules per mole. So here we have the factors that affect the ionisation energy. So these are the factors that make the ionisation energy either be larger or smaller. And the first one is the nuclear charge. So the more protons you have in the nucleus, the more positive the nuclear charge is going to be. And because you've got a more positive nuclear charge, it's going to attract an electron more strongly, which will make the ionisation energy increase. So the bigger the nuclear charge, the bigger the ionisation energy. The second factor that affects the ionisation energy is the distance of the electron from the positive nucleus. So you've got an electrostatic attraction between the electron, which is negative, and the nucleus, which is positive. The further away that electron gets from the positive nucleus, the less the strength of the force of attraction is. So the bigger the atomic radius, the smaller the ionisation energy, because it will take less energy to remove that electron because it's more weakly attracted to the nucleus. Then thirdly, you have the amount of shielding between the positive nucleus and the outer electron. So if you have inner shells of electrons, those clouds of negative charge will shield the positive nucleus from the outer electron and vice versa. So the outer electron won't feel as much of the force of the positive nucleus as it would if those inner electron shells weren't there. So the more shells of electrons you've got, the weaker the attraction between the nucleus and the outer electron, and therefore the ionisation energy goes down. So now we need to look at the trends, and as you go down a group, three things happen. So the first thing that happens is that the nuclear charge increases, because as you go down a group, you've got more and more protons, so nuclear charge has gone up. This would tend to give a higher ionisation energy, the reasons we discussed before. Secondly, when you go down a group, the atomic radius gets bigger. So this means the distance of the electron from the positive nucleus has increased. So because the distance has increased, there's less attraction, so you've got a lower ionisation energy. Then thirdly, you've got the amount of shielding between the positive nucleus and the outer electron. Because you've got the atomic radius is bigger, you've got more shells of electrons between the outer electron and the positive nucleus. Therefore, there's more shielding, so that outer electron is not going to feel the full force of the positive nuclear charge. So therefore, you're going to have a lower ionisation energy. Now you can see here we've got three factors which influence the ionisation energy, and two of them would tend to give you a lower ionisation energy, and one of them would tend to give you a higher ionisation energy. Now overall, we find that 2 and 3 are more important. So the ionisation energy is lower as you go down a group because of factors 2 and 3. And it turns out the increase in nuclear charge isn't that important. So the next trend you need to worry about is going across a period. So going across a period, the nuclear charge increases. This would tend to give us a higher ionisation energy. The distance of the electron from the positive nucleus goes down. As you go across a period, the atomic radius decreases. So this would tend to lead to a higher ionisation energy because the electron's slightly closer to the positive nucleus, so it's going to be more difficult to remove it. Then lastly, the amount of shielding between the positive nucleus and the outer electron. In this case, as we go across a period, it's going to stay the same, as the electrons are entering the same shell, so there's no change in that. So we have one factor that doesn't affect it, and 2 that make a higher ionisation energy. So as you might imagine, 1 and 2 are the most important, which means that as you go across a period, you get a higher ionisation energy because the electron's more difficult to remove. However, having said that, there are a couple of exceptions. So if we look at the ionisation energy across a period in more detail, although the general trend is to increase, there are 2 exceptions, and these are very popular exam questions which students often get wrong, so make sure you completely understand these and remember them. So the first exception is magnesium to aluminium, and that goes down, even though you would expect it to go across for the reasons we've discussed. And the reason it goes down is that the outer electron goes into a free p for aluminium rather than a free s. And as you know from when we did electron configuration, the free p orbitals are slightly further away than the free s orbitals. So they're slightly higher energy, so they're slightly easier to remove. When we look at phosphorus going to silicon, you also get a decrease in ionisation energy, but it's for a different reason. So in phosphorus we've got free p free, so we've got in our free p orbitals there's a single electron in each of them. When we go to sulfur, we've got 4 electrons, so now one of them has had to pair up with one of the others. So you've got 3 orbitals, 2 of which have got a single electron in, and one which has got two electrons in. So because the 4th electron has had to go into an orbital which is already occupied, there's going to be some electron-electron repulsion there, and that repulsion makes it slightly easier for the electron to be removed, which is why the ionisation energy goes down. Okay, so the next thing we need to look at is successive ionisation energies. So when you go from +1 to +2 to +3, +4, etc. And there's 2 important points about this. The first is that each electron that's removed takes more energy, and that's because the first electron is going to be removed from a neutral atom, whereas the second one, you're going to be taking it from something that's already positive, so it's going to be more difficult to remove the ion. It's going to be harder. So each successive ionisation energy is going to go up. Now the second thing about these successive ionisation energies is that we can use them to predict what group the element is in. And that's because the electrons in the outer shell are going to be easier to remove because they're further away from the positive nucleus, so there's more shielding. So when you go to an inner shell, you're going to see a large jump in ionisation energy, and that's where we've started a new shell. And the best way to get to grips with this is to look at some examples. So on this slide I've highlighted with a red box where we've got a large jump in energy. So the magnesium, for example, the first ionisation energy is 736, then 1450. So you've only got a jump there of roughly around 700. However, going from 2+ to 3+, there's a huge jump. You've now got a difference of about 6,000. So you've got a massive increase in the amount of energy required, and that's because the first 2 electrons are from the outer shell, and once they've been removed, the next electron, so that 3rd electron, is going to have to be removed from an orbital that's closer to the nucleus, so it's going to feel the effect of that positive charge a lot more. So by looking at those ionisation energies, we can see there's a big jump between 2 and 3, so we can see that it's in group 2. So if we look at silicon, we'll see the same thing. Silicon's in group 4, so from 786 to 1580 to 3230 to 4360, there's not much of a jump. 1000, 1600, not that much. Then between 4 and 5, there's about 12,000 difference. So that's where there's a big jump, which means those first 4 electrons were from the outer shell and the 5th one's from the next one, so we can tell it's in group 4. If we then look at aluminium, you can see again 577 to 1800 to 2700, there's not much of a difference. But then there's a huge difference between 2740 and 11600. So that's where the new shell has been entered, that 4th electron, which means it's in group 3. So if we look back at our lesson objectives, you just need to look over these and make sure you've met them, and as usual, if you haven't, go back and watch the video or go and read your textbook or whatever online notes you like looking at to make sure that you've covered them. So you need to be able to define the first ionisation energy and successive ionisation energies, explain the factors that influence ionisation energies, and predict the number of electrons in each shell as well as the elements group using successive ionization energies.